So last time we were left off in the middle of considering what happens when we have this interesting collision between an incoming wave packet, which describes the probability of a particle that's coming in with an energy E, and that energy E we've chosen to be lower than the height of a simple step in potential of height v naught that happens in our potential function v of x. And of course, we're expecting then that these particles are going to be bounced off of the edge of this step. And we had studied the incoming piece of the situation, and we were just about to begin to consider what happens for the particles when they bounce back. But we need to call back to mind quickly various mathematical details of the solutions we were dealing with so that we can now complete that analysis. So as you recall, when I have any potential V, if I've got pieces of the potential where things are constant, then I can characterize those behaviors. The first region was a classically allowed region because the energy is greater than the potential. There's enough energy to be there for a classical particle. That then is characterized by oscillatory type behaviors, characterized by a wave vector, which we had determined to have the following form. In region 2, there's not enough energy for a classical particle to be here. This is what is known as a classically forbidden region. It follows a similar type of formula, but now what we get is the exponential decay constant, which we labeled alpha 2. We also noted that these two constants are not independent of one another. If you square them and add them together, you will see the square roots would disappear, the e's would cancel, and I get simply this constant 2m times the potential over h bar squared, which we define then as a handy constant, which we will call q naught squared. We use that definition because then there's this very nice mnemonic that helps us remember the relationship among these quantities. Q naught is a constant, but k1 squared plus alpha 2 squared gives us q naught squared, so it makes a nice right triangle type diagram. Once we had this allowed us then to solve the time-independent Schrödinger equation, which is a key component of our time-dependent solution, which consists of these weights, which then give us a particle packet that's coming in with all of its wave vectors k1, very close to some given value k0 that represents the incoming particle momentum, times the states, or the pure energy states, which solve the time-independent Schrödinger equation, times the dates, or this time evolution factor. The particular solution that we had found for the time-independent Schrödinger equation had the following behavior then. We have our oscillatory behavior in region 1 for x less than 0. This is a plot of phi of x. Out here then we have a wave vector given to us very nicely actually by 2 pi over k1, a wavelength, 2 pi over k1, where k1 is the wave vector. In region 2, in the forbidden region, you can see that in our solution we have an exponentially decaying behavior, as I've sketched for you here. And of course, to match our boundary conditions, we have to match value and slope at the joining point. The last thing I wanted to point out is that the characteristic distance for this type of exponential behavior is not a wavelength, but what we call the decay length of the exponential. You either think of it as the point where the exponential decreases by a value of a factor of 1 over e. That's the 1 over e decay length. Graphically, that decay length represents the point where if I were to extrapolate my slope to the horizontal axis, the distance that I would have traveled. Either way you want to determine this decay length, the characteristic distance where we can find particles having penetrated into this forbidden region where they're typically not allowed is a distance of 1 over alpha 2. So there is definitely some possibility for our packet to penetrate into this region to undergo this quantum tunneling type behavior. We were then analyzing the behavior of this solution that we've written down, now that we have the full solution. And what we noticed is that in this interesting region where x is less than 0, where I have particles coming in and perhaps bouncing back, I have two independent pieces to my solution, the sum of which then gives me the overall behavior for the solution. And we were just analyzing the first piece of that sum, which is the wave function that we would generate if we only had this positive exponential part. We analyze this in terms of where and when the resulting packet, that is the integral of these weights times just this one state, right, times the time-dependent pieces, not looking at the second part. We applied stationary phase, and we came to a very interesting conclusion. We found that the maximum position of that packet then starts off at very large negative times at well, actually, the actual value that we had for that positive packet, we could write this down. The maximum position for the positive packet as a function of time t was just the velocity times t. So I have this incoming line of slope v0 that hits the origin exactly at time t equals 0, and that packet then would continue on, mathematically speaking. But of course, we had noticed that this solution that we are looking at only applies in the x less than 0 case. So then when it goes off to x greater than 0, I don't see anything from this piece. It goes into that no man's land, so to speak. If I look at a storyboard of before, during, and after the collision process, when time is much less than 0, my packet is centered at some very negative value. So I would see it over here in this region where the solution applies. And I've put a little plus above this peak because that's the peak that's associated with this plus part of the solution. During the collision at exactly x equals 0, this peak would be centered on the origin, so I've drawn it that way, where now the peak is sort of half gone into the mathematically imaginary zone, so to speak, this kind of twilight zone. And then finally, for times long afterwards, I will be at these large positive values, and the contributions from this particular piece of the solution would then completely vanish. Very good. So now it's time to consider the rest of the behavior in this important x less than 0 region. And for that, then, we will now turn to understanding the second piece of the solution, this psi minus function.